All right, next we're going to look at one-dimensional motion in the vertical direction. So in this case, we're going to have an acceleration due to gravity. So if we can ignore the effects of air resistance, an object tossed up or down or simply dropped is only affected by gravity and will accelerate downward at a constant rate. This is called free fall acceleration. The free fall acceleration is independent of the object's mass, density, or shape. So once it leaves our hand, it's only under the influence of gravity, and so this is called free fall. Now, it once was thought that heavy objects fell faster than light objects. Many people even still believe that. This was asserted by the Greek philosopher Aristotle. He even said that a 10-pound object would fall 10 times faster than a 1-pound object. Aristotle, however, just did everything by logic and didn't actually do experiments. Well, the Italian Galileo came along and in the late 1500s did a public demonstration showing that dropped objects of different weights will fall to the ground at the same time when air resistance was negligible. So he took a wooden ball and an iron ball, both about the same size, and dropped them from a very high place and showed that they both fell to the ground at the same time. So that proved that Aristotle was wrong. Now Galileo was from Pisa, and the highest place in the town was the Leaning Tower of Pisa. So there's no historical record of him actually doing this from the Leaning Tower, but the legend is that he did do this from the Leaning Tower of Pisa. The record says that he did it from a high place, and that was the highest place in town, so it was likely he did it from there. There is a YouTube video by Brian Cox on the BBC where he visits the world's largest vacuum chamber and does a dramatic example of dropping a bowling ball in a feather under vacuum. So I encourage you to look at this video. I will include a link to the video in the description below. So take a look at that. It's quite dramatic and very interesting to see. All right, so we will look at a couple of examples of free fall motion or vertical motion in the vertical direction. So we'll use the small g to represent the acceleration due to gravity. The value of g will vary slightly with latitude and elevation, but at sea level in the mid-latitudes, we use the value of g as 9.80 meters per second squared, and the acceleration is downward toward the center of the Earth. Now that variation with latitude and elevation and local density is very, very small. So we'll just use the 9.80 meters per second squared. And as long as you don't get very high above the surface of the Earth, that value will stay at 9.80 meters per second squared. And so we consider that value of the acceleration as a constant. Using 9.80 meters per second squared for g and assuming it's constant, then the equations of motion become what's shown here on this slide. The position y is a function of time, is our initial position y naught, plus any initial velocity y sub 0 times time t minus 1/2 gt squared. Now notice the reason we put the minus sign in the acceleration term is because the acceleration is downward. So we're using the convention that upward is positive and downward is negative. Then the velocity as a function of time equals v0 minus gt, and then of course if we eliminate the time between those two equations, we get the third equation, v squared equals v naught squared minus 2g delta y. Now note we use the negative sign explicitly in the equations. So don't put in minus 9.8 meters per second squared for g. Just use the positive value for g. So these are our equations of motion for free fall. Okay, so here's our first example. You drop a stone from a high cliff and it falls 48 meters below. So part A, we want to find how long does it take to fall to the ground, and B, how fast will it be going when it hits the bottom. All right, for part A, we want to find how long does it take to fall. Well, we know how far it falls, and we know the acceleration due to gravity, and we know we're dropping it from rest, so we just use the position as a function of time and solve for the time. So position as a function of time, we have y equals y naught plus v naught t minus 1/2 gt squared. All right, so we're going to say the top of the cliff, we're going to set that to be y equals 0. So then at the bottom of the cliff, the y will be negative 48 meters, the negative sign because it's down. So we have negative 48 meters equals, we have 0 for the y naught. We're dropping it from rest, so our initial velocity is also 0. So all we have is the negative 1/2 gt squared term. So I've put in the 9.80 meters per second squared for g, and we're going to solve for the time t. So half of 9.8, of course, gives me 4.9. So I've got negative 48 meters equals minus 4.9 meters per second squared times t squared. And then solving for t, we get 3.1 seconds. So that's how long it takes to fall. So now part B, how fast is it going when it hits the bottom? Well, now we know how long it takes to fall, so all we have to use is the velocity as a function of time to get the velocity at the bottom, or the speed at the bottom is what it asks. So our velocity as a function of time is v equals v naught minus gt. We're simply dropping it from rest, so our initial velocity is 0, so we just have v equals the negative gt. So I put in the 9.80 meters per second squared for g and the 3.1 seconds for the time to fall, and we get the velocity equals negative 28 meters per second. The negative sign means the velocity is in the negative direction or downward. The speed is just the positive value of 28 meters per second. Velocity includes the direction. Speed is simply how fast. So we've got the answer to the problem. Here's another example. Throw a ball up while standing on the edge of a 200-meter cliff. The ball goes up, then it falls down to the bottom of the cliff. If the initial velocity is 11.2 meters per second upward, A, how long does it take to reach its maximum height? B, what is the maximum height above the top of the cliff? C, where is it after 2 seconds? D, how fast is it at 2 seconds? And E, how long does it take to hit the ground below? So we're going to go through this step by step. So the first part, how long does it take to reach the maximum height? Well, if you take an object and you throw it straight upward, what happens to it? Well, on the way up, it's going to slow down, and then eventually it comes to a stop momentarily and then comes back down. So when it reaches its maximum height, it momentarily stops. So its velocity is 0. So at the maximum height, the velocity is momentarily 0. So using the velocity as a function of time equation and knowing that at the maximum height it briefly stops, we can find the time it takes to reach the maximum height. So we write v equals v naught minus gt. Solving for the time t, we get v minus v naught divided by minus g. Then we plug in the numbers. If we say our initial velocity is 11.2 meters per second, that was given. At the maximum height, the velocity is 0, because it momentarily stops. We have minus 11.2 meters per second divided by negative 9.8 meters per second squared. The meters cancel out. One of the seconds cancels out, and we get 1.14 seconds. Rounding it to 2 significant digits, we get 1.1 seconds. So that's how long it takes to reach the maximum height. Now, part B, what is the maximum height? above the top of the cliff. All right, well, we know how long it takes to reach the maximum height, so now we can write the position as a function of time and put in that time. So we're calling the top of the cliff as 0. The initial velocity is 11.2 meters per second upward, so that's positive, times the time, 1.14 seconds, minus the 1/2, which is 0.5, times the g, times the time squared, and I crunch those numbers, and we get 6.4 meters. So that is the maximum height above the top of the cliff. So see, once we know the time it takes to reach the maximum height, it's very easy to get its position at that time. Okay, so part C, it says, where is it after 2 seconds? All right, so we just use the position as a function of time equation and use 2 seconds for the time and find out where it is. So again, our initial position, y0, we're calling that 0. So we have y equals the v0t minus 1/2 gt squared. So we have 11.2 meters per second times the 2 seconds minus the 1/2 g and the 2 seconds squared. I crunch those numbers, we get 2.8 meters. Okay, so now notice that the time to reach the maximum height was only 1.14 seconds. So at 2 seconds, it's already reached the maximum height. It's coming back down. So it's on its way back down, but it's still 2.8 meters above the top of the cliff. So part D, how fast is it at 2 seconds? All right, so to get how fast it is at 2 seconds, we use the velocity as a function of time equation and use 2 seconds for the time. So we got v equals v0 minus gt. So we got 11.2 meters per second minus 9.8 meters per second squared times 2 seconds. And that gives us, for the velocity, a negative 8.4 meters per second. So the negative velocity tells us that it's going down. The speed then, of course, is the positive value, since speed is just how fast without considering the direction. So the speed is 8.4 meters per second. But the negative velocity tells us that the ball is going down. All right, now part E. How long does it take to hit the ground below? Well, we're calling the top of the cliff y equals 0. So at the bottom of the cliff, that's y equals negative 200 meters, because we're saying down is negative. So we use the position as a function of time equation and put negative 200 meters in for y. Our y0 is 0. And then we have the v0t minus 1/2 gt squared. So plug the numbers in for those and solve for t. So we have minus 200 equals 11.2 meters per second t minus 0.5 times 9.8 meters per second squared times t squared. So we have a quadratic equation. So put all the terms on one side and simplify them. So we get 4.9 t squared minus 11.2 t minus 200 equals 0. Now we can use the quadratic equation to find a value for t. Well, the quadratic equation, of course, gives us two values for t. We get 7.63 seconds or negative 5.34 seconds. Well, we're not going backward in time, and so we don't want the negative value. We want the positive value. So that means it takes 7.6 seconds for the ball to reach the bottom of the cliff. Now finally, the last part, how fast is it going when it hits the ground below? Well, since we know the time it takes to hit the ground below, we can use that time in the velocity as a function of time equation and find out how fast it's going. So we have v equals v0 minus gt. V equals 11.2 meters per second minus the g times the t, which is 7.63 seconds. And we get the velocity equals minus 63.6 meters per second, or the speed then is about 64 meters per second. Again, the negative sign tells us that it's traveling downward, but speed is only how fast without the direction. So the speed then is 64 meters per second after rounding it to 2 significant digits. Okay, so that's the end of this example. So you can see by carefully drawing a diagram. Again, you don't have to be an artist, and choosing a coordinate system. It's very easy to just apply the kinematic equations, the position as a function of time and velocity as a function of time. And just be careful of the signs, and choosing up is positive and down is negative. All right, in another video, I'll do some more vertical motion problems. And then after that, we'll move on to motion in 2 dimensions. Hi, Dr. C here. Thanks for viewing this video. And please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions. And I thank you for your support of this channel. I've also included a link to the next video in this series.